So we're going to start off talking about position functions and average versus instantaneous velocities, or average versus instantaneous acceleration. Okay, so we need to understand what an average instantaneous or average versus instantaneous means. Okay, so an average acceleration is the tangent or a secant line slope, right? So it has 2 points, and we're looking for the slope of the secant line, often called a difference quotient, like we had talked about earlier, versus the instantaneous velocity, which is the slope of the tangent line. So whenever we're asked for instantaneous velocity, we will be doing a derivative, where when we're finding average, we will be doing a slope function or a slope calculation. Standard Algebra 1 slope stuff. So there is our average velocity equation, right? So average velocity is the slope of the secant line. And since the secant line has 2 points, our formula will also have 2 points in it. Okay, it looks an awful lot like a slope formula, right? This is y minus y over x minus x, which is exactly what it is. Okay, versus our other one, which is instantaneous rate of change, which is the derivative of your position function. So we have to be given the time when we want to find the instantaneous velocity, and instantaneous velocity is the slope of the tangent line, because you only need to have 1 point for instantaneous velocity. So let's see how we can apply it with these questions. Here we have our position function. Okay, it is e to the t times sine t, where p is measured in centimeters and t is measured in seconds. Okay, it's important because, look, we want appropriate units of measure. On your AP test, you get points for putting down the units. Okay, you get 1 point for the answer and 1 point for the units, especially when it comes to these type of questions. So let's see, average velocity from t equals 1 to t equals 3. Okay, so we want average velocity, AV, V, that's weird. Average velocity. Okay, so this is P of 3, that is an awful 3. P of 3 minus P of 1 over 3 minus 1. So we start with the difference quotient, P of 3 minus P of 1, and then we show the substitution into our position formula. And since this is a gross looking thing, I'm going to use a calculator to round the answer to 3 decimal places. My calculator says the answer is 0.274 when I round to 3 decimals. So then what about the units? So on top, position is in what type of units? Position is centimeters, and the denominator, the time, is in seconds. So this is centimeters per second. Or if you want, cm/SEC, or you can write it as a more proper fraction also. Centimeters per second are the units. So on the AP test, they would give you 1 point, probably for showing this, 1 point for the answer, and 1 point for the units. Okay, so don't forget about the units at the end. Versus question 2, what is the instantaneous velocity at time t equal 1.5? Okay, so instantaneous velocity means we need to take the derivative of p. Okay, so p prime of t, looks like we're going to be using a product rule since it's e to the t times sine of t. I'll be right back with that answer. Okay, using your product rule, this is the derivative of our position function, e to the t sine t plus e to the t cosine t. And now I simply have to replace t with 1.5, and I'm going to use my calculator to do that and get the answer. Rounding to 3 decimals, that's 4.787. Okay, but what are our units? This is velocity, so our units are? Centimeters per second. Centimeters per second. Okay, so the connections, if we're trying to find the secant line, then we're using the difference quotient or the average rate of change. Okay, so secant line is average velocity, and instantaneous velocity corresponds to the derivative at that point. Okay, so we have an average or an approximate velocity, and then we have the derivative, which gives you the instantaneous velocity at that given time. So there's a little something about velocity. So let's pause for a second, and I will bring up something and we'll talk about acceleration. So for acceleration, we still have to have a position function, but then we know that the velocity function is the derivative of the position. Okay, so velocity is the derivative of the position function. Okay, if that's true, then the average acceleration, which I'm just going to call ACC, because acceleration is a really long word to write. So if you want to shorthand it, just know that ACC stands for acceleration. The average acceleration from time t equals a to b is once again going to be given to you by a slope formula. Okay, that would be the velocity at b minus the velocity at a over time b minus time a. So very similar to our velocity formula, but velocity comes from position, where acceleration comes from velocity. Okay, and remember, velocity is the first derivative of your position function. So acceleration is going to be the second derivative of position, or the derivative of velocity. So average acceleration, right, depends on your velocity, but instantaneous acceleration at time t, right, at a specific time t, is given to you by the derivative of your velocity function. So acceleration is equal to your velocity function, which is the second derivative of position. Okay, so all of these functions are going to be twice differentiable so that you can actually find the acceleration of your function at a certain point in time. So once again, we have an average versus an instantaneous. So we have a formula versus a derivative. Okay, so I'm going to do these two. You can pause the video and try them yourself with the same function right there. Okay, average acceleration is the position of velocity, right? V of 3 minus V of 1 over 3 minus 1. So I substitute 3 into my velocity function, and I substitute 1 into my velocity function, and I divide it by 2, and I got this as my acceleration. Oh, what are the units of acceleration? Meters per second, or centimeters per second, right? Centimeters per second. Because on top I have centimeters per second, that's my velocity units, and on the bottom I'm still dividing by seconds again, my time units. So centimeters per second are the units of acceleration. And then when I take the derivative of my velocity function, okay, I get 0.634, and my units are centimeters per second. Okay, so average acceleration is a slope of the velocity function, which is a derivative of position. And average instantaneous acceleration is the derivative of velocity, and it still has the same units. Okay, so let's summarize some things that we've learned, hopefully, and some things about our position function. Okay, so that's how our functions that we have been dealing with talk about our position curves. Okay, function goes with position, first derivative goes with velocity, second derivative goes with acceleration. Okay, so let's see, what about the movement? What about the motion of our particles? If our velocity is 0, what is the position of our particle doing? And so on. So then this is how our sign, right? These are the signs of your velocity. If it's 0, if it's positive, if it's negative, and if it changes, then this is what it's doing on our graph. Okay, if we have 0 velocity, we're stopped. If it's positive, we're moving to the right. If it's negative, we're going left. And if it changes, you go left to right or right to left. Okay, so there's some things about our acceleration. So what can we tell about our acceleration based upon the velocity graph? Okay, so there's 5 things we can do here. So I'm I'm going to pause and fill them all in, and then pause after that so you can write them down. Okay, so there's our summary of the acceleration, which is the derivative of velocity. 0, positive or negative, or if we're doing a sign analysis and it changes from positive to negative, that means your velocity is changing from increasing to decreasing. Okay, and if it's 0, of course, your velocity is constant. So our next questions are asking about this graph, right? And this is the position graph. So anytime we're asked to justify your answer, we're going to be using the position in order to justify our answer rather than the slope or the second derivative. Okay, so what about the graph can we say in order for we can find out when is the velocity equal to 0? So for the first question, we have point B and point D as your velocity equal to 0, right? The tangent line would be horizontal, but we can't say anything about the tangent line because this is a position graph. So we have to use position wording. So the position changes from increasing to decreasing. So here we have y values that are going up to point B, and then we're now going down, right? The y values are decreasing, so that means we had a maximum value here, or a 0 at the top. And then we have decreasing y values to this point, and now they're increasing. So whenever we change from increasing to decreasing, we're going to have a 0, and that's the verbiage for a position graph. Now, if this were a velocity graph, yes, we would have positive slopes and negative slopes, and that would tell us the reason. And then part C is where the acceleration is 0, because that's where your graph changes from concave down to concave up. Okay, we start from an N and we'll start making a U at point C. Okay, so the other questions are about velocity. So we're either looking for, well, let's see what we're looking for. Velocity is positive. From negative infinity to B, our y values are increasing. So that's where our velocity is positive. And then again from D all the way up past E to positive infinity, once again, that's where our y values are increasing, so that is where our velocity is positive. Okay, and the exact opposite for velocity negative. It's going to be between B and D, because that's where your graph is decreasing. The y values are decreasing there. So when we're looking at velocity, we're looking at when is the graph increasing. Okay, or decreasing. So velocity is about where the y values are going up or y values coming down, and acceleration is all about concavity of the graph. Is your graph concave up or is your graph concave down?